Hello everyone, welcome to our evaluation section of the tutorial. The talk will be about evaluating weakly supervised models. I'm the speaker today, Songjano. Why do we want to do evaluation? Well, we do evaluation because we want some ranking in a quantitative way. That means we need to position our machine learning method in the context of compared numbers, like random chance or prior state of the art or human level performance, or if our method is really approaching the theoretical upper bound. So evaluation could also go wrong. And what is the cost of wrong evaluation? This is an example from deep metric learning in the past few years. From papers at face value, the performances seem to increase over time. However, when you correct the wrong evaluation practice in the previous years, you don't actually see the same kind of improvement anymore. In fact, there was nearly no improvement in the more than 10 years, if you also count the contrastive and triplet losses from 2006. The cost is twofold. For researchers, they have put a lot of time on working on a metric that doesn't give you much information. This could be interpreted as an opportunity cost as well, because they could have worked on something that's more important and that's more real challenge. As practitioners who are looking for good metric learning methods, they're misinformed to select something that's actually suboptimal. And this could also incur the cost of neglecting a simple solution, simple baseline that's working as good as the recent, more complex methods. And this kind of evaluation scandal is not rare in computer vision and machine learning tasks. Here's an assorted, selected list of such papers. So the domains cover face detection, zero-shot learning, semi-supervised learning, unsupervised learning, self-supervision, image classification, syntax recognition, weakly-supervised object localization, deep metric learning, natural language question answering, and so on. And we'll look into why this kind of wrong evaluation happens. What are the recipes for making the evaluation wrong? Maybe the first easiest way to get it wrong is everyone writes their own evaluation metric code. In papers, you write your evaluation metric in mathematical terms, and probably the mathematics are equal across all the papers. But at the implementation level or the code level, there can be non-trivial design choices you have to make for your evaluation code. For example, for computing average precision, you have to handle the NaN case where you divide 0 by 0. This happens in the high confidence beans. And depending on how you treat those undefined numbers, you will get different performances for your methods. The second typical failure mode for evaluation is when you confound multiple factors when you compare something. So in this example of deep metric learning benchmark, it looks like you're improving over time by improving the loss function. However, if you actually look at the architecture behind the experiments, you see that there's a big jump in the baseline, in the backbone architecture from GoogleNet and Inception to ResNet. And actually, ResNet gives you much better scores than the previous models, and therefore the gap can also equally be explained by the jump in the backbone architecture. So when you compare multiple when you compare methods, you have to fix everything else saying but the factor that you want to compare. For example, the loss in this case. And when you also compare performances or accuracies, you might be hiding another important axis. Here's an example of syntax recognition. From the face value, it looks like rare is performing much better than Rosetta here. However, this improvement comes at a great cost, which is more evident from the extended axis here. So you're using more than 4 times the latency for rare method compared to Rosetta. If you think about this added complexity, maybe Rosetta is more appealing than rare. So when you compare performances, you should also report how much extra resources you're using. And this is the case when you have training. In the training set, you have test set examples as well. This happens for natural language Q&A from a recent paper on arXiv. For those 3 widely used datasets for natural language Q&A, they have discovered that there's a significant degree of overlap between training and test set answers and questions, sometimes more than 50%. And the result of that is quite striking. For the existing methods, the performances are not really reliable anymore, because if you break down the scores to different splits of the test set, where the first split is where the questions overlap with the training set, and the second is when the answers overlap with training set, and third is where there's no overlap. It is striking that there's actually no reasonable performance for BART on the case where it actually have to generalize to unseen question and answer pairs at 0.8% accuracy. And if you actually compare the total accuracy of BART against the nearest neighbor baseline, where you actually do the memorization more explicitly, you realize that nearest neighbor baseline is beating this previous work. This means that BART has not really learned much beyond memorization. So the rule of thumb for training and test splits is you have to split them. They should be disjoint. And third similar pathological case for evaluation is when there is no validation set. This has happened in CIFAR and ImageNet classification benchmarks. So they have used the test set for making design choices and tuning hyperparameters over time, over a long period of years. And the result of that is this. When you prepare a second test set with the same distribution, but with different samples, then the previous performances in the original test set do not transfer to the second test set. Here are the results. So this is CIFAR and this is ImageNet, and you're comparing the original test accuracy to the accuracy on the new test set. The black dashed line is when the 2 accuracies match, and the blue dots here are the models proposed in the recent years. And it turns out that the blue dots are far below the x equals y line, meaning that the accuracy seen in the original test set is not observed anymore in the new test set. So the methods, the design choices have overfit to the specific test set over time, because the validation set was missing. So the best practice is to introduce validation set and only do the design choices in the validation set. So what is this talk about? Are we going to talk about what can go wrong with evaluation? No, we want to go more specific, and we want to study what can go wrong with weakly-supervised X evaluation, like general weakly-supervised learning tasks. What is so special about weakly-supervised learning tasks? There are added complications. So we start off with the regular train-var test splits for machine learning task. So we describe the three splits like this. So training set is used for model fitting, validation set for model design choices and tuning hyperparameters, and finally test set is sacred. It should not be touched for anything else but reporting final numbers and comparing across different methods. So let's see how that goes for weak supervision case. We also have train val test sets. Okay, but the training set now only has the weak supervision. And the methods are required to only use the weak supervision during training, so you're going to fit the model using weak supervision over the training set. The tricky part is validation set. For validating your weakly supervised model, you somehow need some kind of a final task performance, right? So you need some full supervision to measure your performance. So far there was no solid agreement on how to make use of the validation set for weak supervision setting. Okay, so there's some hint of problem here. And now the test set is the same. So there are full supervisions, full annotations, but this is going to be used only for reporting final numbers and comparing across methods. So yes, again, back to the training set. Training set is weakly supervised, and you're only required to use weak supervision on principle for weak supervision models. And what people do with validation set is they usually use the validation set for tuning hyperparameters. And there's a lack of unified agreement on how to use that set. And because of this lack of agreement, people use the validation set in different degrees. And this leads to a wide range of degrees of extra information they use for training the weakly supervised models. And this leads to unfair comparisons. Even worse, in many weakly supervised benchmarks, there's no validation set. And what people do is they tune their hyperparameters over the test set using full supervision. So this has two problems. One, you're implicitly tuning on the test set and overfitting to the test set over time. But this is problem shared by regular machine learning tasks. But probably the more important issue is that you implicitly use full supervision. And this is against the philosophy of weak supervision. And these issues are not widely known in the weak supervision community yet. So I review a lot of papers from this area and read a lot of papers as well. But surprisingly, many researchers and practitioners are still not aware of these evaluation issues. Many of them are also aware of this issue, but there's no, as I said, full agreement on how to fix this issue. So I hope this tutorial works as a starting point of discussing how to make use of the validation set and how to make fair evaluation for weak supervision and future directions for this field. I think it's good to introduce a specific case for studying this weak supervision evaluation. And we choose weakly supervised object localization as the case study because this is sort of the minimal working example for general evaluation issue with weak supervision. Because you see the same problem in Weakly-supervised semantic segmentation, object detection, instant segmentation, or semi-supervised learning, or unsupervised disentanglement, self-supervision, as well as zero-shot learning. The other motivation for working on WSOL is because of its popularity, more than 100 papers for the last 5 years, and this is widely applied in many tasks, including other more complicated weakly-supervised tasks. This is our paper evaluating weakly-supervised object localization right from CVPR 2020. So we, before starting the studies, we first define what WSL is. It's weak supervision with object localization. So now the question is, what is object localization and what do we really mean by weak supervision? Because there could be multiple possibilities for this. So for answering the question of what is object localization, we start off with a simple task of single label classification. Everyone should know what this is, but I'm explaining this again for the sake of the flow. Single label classification asks the question, what is in the image? The answer here is cat. The key assumption is that there should be one class per image. If there are more than one classes per image, then it should be called multi-label classification. So object localization is based on this single label classification setup. So there should be one class per image. But now the question is, I know that there is a cat, but the question is, where is the cat? So yeah, again, two assumptions here. One class per image, and two, the model should know what the class is. And the only task is to point out where the cat is. The format of output could be a point landing on the object region, or a box enclosing the extent of the object, or it could also be a mask. In this talk, we'll assume a mask output throughout the talk for object localization. Now the question is, how is object localization different from, for example, semantic segmentation? For semantic segmentation, you assume multiple objects present per image. It could be more than one. And the ground truth class is, of course, not given, and the whole task could be seen as a pixel-wise classification. What label do we assign to this pixel? And it's also different from object detection for the same reason. There could be multiple object classes per image, and the ground truth class is not given, and you have to separate instances in this case. Now we answer the question, what do we mean by weak supervision? By weak supervision, what we mean is image labels. So in the context of this, this nice diagram from Hakan, the training supervision is image labels, but the final task is foreground background mask. Okay. And the full supervision we are going to refer to a lot of times throughout the talk will mean when you train with foreground background mask and then test with foreground background mask as well. So now we go to the next subpart where we study WSL methods in detail. How are they trained and evaluated in practice? So again, there is no validation set for WSL benchmarks. So we are going to study how, for example, class activation mapping is trained and evaluated in those benchmarks. Over the training set, what's happening is you can only use the weak supervision. So you can only train a classifier, and you formulate your classifier in this way, where you have an input image that's mapped to a score map, and then you have some global average pooling or any kind of spatial pooling, and then you compare this class prediction output with the ground truth class label. Okay, so this is the same classification training, but at test time you replace the global average pooling with thresholding per pixel, and that's going to give you a foreground background mask. And here we use full supervision to measure the performance over the test set. So this looks like a clean procedure, right? CAMP has not used any full supervision and has only relied on weak supervision for training the model, right? Probably not. I'm gonna talk about like 4 versions where things could go wrong. So the first naive version of how we might be using full supervision implicitly. And the user in this case is asking which threshold do we choose for thresholding here. And the researcher decides to just use 0.5 because why not? And that gives you test set accuracy of 45% using the ground truth mask on the test set. And then he thinks, I need to beat the previous CVPR of 51%. And we probably want to choose something lower to improve the accuracy, and decides to use 0.2. When he chooses 0.2, then he gets 52% test set accuracy. And now he's happy and goes on and writes a paper on this. Okay. You notice some hint of what could go wrong, right? You're tuning the hyperparameter over the test set using the full supervision, right? So the second person here realizes the problem and decides to not tune the hyperparameter on the test set. In fact, he decides to never touch the full supervision at all. Instead, what he does is he's going to inspect a few outputs in the training set using human inspection. Yes, this is also using some kind of human in the loop, right? So some people might think this is against the weak supervision policy. And the third person comes in and says, okay, we are not going to use human in the loop or test set validation. We are simply going to adapt whatever hyperparameters have been used in previous papers. And therefore, it's not our fault that we are using some hand-wavy solution for fitting the hyperparameters. We are just using what's out there. Okay. And of course, the final type of people, they do some black magic during experiments. And then in the paper, they don't fully disclose how they reached this solution. We just use threshold 0.5, full stop. So in summary, there are common strategies for getting good WSOL, or more in general, WSX performances. First, introduce many hyperparameters. And second, tune the hyperparameters with one of the following strategies. You do validation on the test set, or you do human in the loop, or just say, it's not our fault, we just use the numbers from previous papers, or you do some black magic. And this is actually happening in previous WSL papers with hyperparameters far more than just threshold. Yeah, for example, SPG has 1, 2, 3, 4, 5, more than 9 hyperparameters and thresholds for to be tuned. And this is not just a WSL problem. In WSS and WSOD, WSIS, you have the same kind of problem in different literature. Why is this happening? Is this because the researchers are doing something wrong? No, we don't try to blame the researchers for this. Instead, we argue that extra information is essential for training weak supervision models. In a sense, weak supervision is ill-posed and cannot be solved without utilizing something extra other than the weak supervision itself. Here's an example for WSL. We argue that WSL is not solvable, even with infinite amount of data, if there is a correlation between the classes and the background cues. For example, if you look at doc images, typical dock images don't have docks feet. Instead, they are floating on the water. So water pixels are more correlated with the dock class than the dock's feet. And therefore, the model has no way to figure out if dock's feet belongs to the dock class or the water pixels belong to the dock class. So because of this correlation, if that correlation persists in even in infinite amount of data, you still have the same problem. And therefore, the four strategies people have been using now make sense, because they need to use some kind of extra information. So what we suggest in this talk is to legalize the use of full supervision during training, but we keep that in control. Because we need to make a fair comparison across different methods. So what we do is we equalize the amount of extra information for every method, and we put the same computational budget for finding the hyperparameters. And the solution specifically is to introduce the validation set, a small amount of full supervision for every method. So this is the roadmap for the rest of the talk. First, we talk about how to introduce the validation set for WSOL, and then we re-rank the recent WSL methods in the context of this new validation set and new hyperparameter search strategy. And then we talk about future directions for WSL and Weakly-supervised tasks in general, given the inevitability of extra information. So now we introduce the validation set for WSL. So there was no validation set, but now we introduce the validation set with full supervision. And now we let the WSL method search hyperparameters over the identical validation set. And this is the apparatus for ensuring the equal amount of extra information for every method. So this was how the field looked like before we came in. There was a training set and test set for ImageNet and CUB, but no validation set. But we introduced the validation set for ImageNet and CUB, and we also introduced a new benchmark based on open images, also with the validation set. This is how it looked like before our cleanup. They did all different methods for tuning the hyperparameters, but now we fixed the method. We do random search over the hyperparameters on the validation set, and we do 30 iterations each. And this is how it looked like. These are reported results in existing papers, and as we see, there is no unified metric. People use different data sets depending on the paper, and depending on the paper, they use different architectures. And this impedes fair comparison of WSL methods. So what we did was we unified the architecture and data set and metrics for WSOL, and we filled in all the missing cells here, and we cover 3 times 3 times 6 experiments, totaling 54. So this is the result. This is how it looked like before we came in. Reported results in respective papers, and there's a small warning here that different architectures are compared in this plot. And now, after our cleanup, we observe these kind of results. So compared to the previous slide, where you see a bit of increase in the performances over time, well, but yeah, of course that degrades a bit in the later works, but overall trend was increasing. But now you don't see that overall increasing trend. So this is the average of ImageNet, CUB, and open images. And this is quite striking that CAM, the 2016 method, is still the best one. And now another question is whether you can use the validation set for something else than hyperparameter tuning. Well, we let the users use the full supervision as freely as they want. So the validation set doesn't have to be used for validation itself. It can also be used for model training. So we also compare against the baseline when we use this small validation set for model training. And this is how the baseline looks like. We use the same CNN model with this format, but with segmentation loss, with pixel-wise cross-entropy on a small number of foreground background masks in the training set. And this is the result. So the Fuchsia learning baseline, where we use the full supervision for model fitting, is greatly beating the best WSL method of CAM. And this happens at only 5 samples per class. So this is a very striking result. This means whether we want to do any WSOL, complex WSOL method. From the results before, it looks like complex WSL methods lose their appeal, because CAM is still simple and effective. And also the Fuchsia learning baseline is also very effective. So if you have if you really want something that's working well, then you should spend some time annotating the full supervision, but very small set, and then tune your model with those samples. And that's going to most likely give you something better than a WSL-based method. And the second implication is the introduction of new phase for WSL and general Weakly-supervised learning research by acknowledging the need for extra information for weak supervision. So now weak supervision is impossible, and we need to use extra information. And now the question is how to make best use of this full supervision. Should we use that for validation, or should we use that for model fitting, or maybe we can use that for something else? And this also opens up the question of okay, if you look on the web, there are many academic datasets with lots of different types of supervisions. Sometimes weak, sometimes strong, sometimes exactly matching your target task, so-called full supervision. So the question is how to combine those multimodal supervision types to transfer to your task. And the other way to think about this is we need extra information, but still we want to minimize the extra information, because this extra information could mean human labeling. So for solving your target task, you instead constrain on the minimal required performance, and then you try to minimize the human labeling cost. And this is another interesting research direction. So this is the summary of possible future directions. So one is you look into hybrid Weakly-supervised X, which is about combining different levels and amounts of supervision for your task. And this is relevant again because you have an abundance of well-curated and raw data on the web with different levels of supervision. And there are exciting, non-trivial research questions. First, you need to set up benchmarks, and you have to think about how to combine multiple supervision modalities. And second direction again is human in the loop. We define the task instead as minimize the extra annotation effort, given that you constrain your method to be at least as good as n% performance on some benchmark. Please see Rodrigo's tutorial talk on human in the loop for this. So here's the conclusion and takeaways from this talk. We started off with the motivation that WSL benchmarks are missing validation, and potentially you have overfit to the test set in two ways. One, you have overfit the specific test set samples, but also you're implicitly using full supervision on the test set. And this adds complications compared to the regular machine learning task evaluation. And therefore, the common strategy that people have been using for getting good scores on WSL and other WSX tasks is first to introduce many hyperparameters and tune them over the fully supervised samples. And this is against the WSL philosophy, but we say this is understandable given the impossibility of the WSOL tasks. And therefore, instead of ignoring the need for full supervision, we need to legalize the use of full supervision through the validation set. And this is good because then you're ensuring the same amount of full supervision for every method. By doing this, we have found that the apparent improvement over the 4 years are actually illusory. And we also remark that the validation set doesn't need to be used for validation. And this opens up a new phase for Weakly-supervised learning research. It could be, you could look at hybrid Weakly-supervised machine learning for looking into how to combine different levels of supervision. Or you could look into reformulate the problem in the dual format, and then you could look into human-in-the-loop tasks. So this is the end of the evaluation part of the tutorial.